Good morning, everyone. This AI and data science revolution that we're all living through is bringing incredible new capabilities for your businesses, but at the same time, lots of risks. And what I want to do is remind all of us of what some of those risks are, and then talk about some of the current research aimed at addressing those risks. Why is AI and data science so important for our enterprise? We've got incredible new capabilities that are helping us to do our business better and in new ways than ever. We have the ability to extract insights from unstructured and semi-structured data like free-form text and tables and charts and graphs with the same facility that used to be reserved for relational databases and spreadsheets. Increasingly, we can distinguish causality from mere correlation, and with it do a much better job of predicting the future. We have sensors everywhere in these smartphones in our pockets, wearable medical devices, our increasingly censored homes, automobiles, and factories. And tremendous new capabilities are being developed for analyzing time series data from these sensors in real time in powerful ways. We have techniques for identifying anomalous data points in microseconds that can help us to shut down equipment before damage occurs, or interrupt a fraudulent transaction at a point of sale before any money actually changes hands. We have unsupervised techniques that allow us, for example, to take a look at data from medical sensors and distinguish running from sitting, from walking, or can perhaps identify a heart attack or a stroke moments before you even experience the symptoms yourself. Natural language processing gives computers the ability to make sense of written and spoken speech, and increasingly to tease out subtle meanings like what are our sentiments and our feelings. And of course, computer vision is touching everything, from identifying images and videos on the internet to recognizing what's going on in a bricks and mortar sales situation. But with incredible power like these and others comes a whole new set of new problems. As all of you seek to apply these technologies in your businesses, you're able to bring hyper-personalization to what you're doing. You're able to optimize your operations. You understand customers better than ever before, and at a more granular scale. What are they going to buy this month instead of next month? Who are the trend setters? What's going to happen in the eastern part of a country versus the western part of the country? And of course, we're all recognizing that data is more important than ever before, but at the same time, we're aware of and concerned about the concentration of data in a small number of very powerful companies. As companies seek to apply these technologies, I see a hierarchy where companies begin by using these technologies internally for greater operational excellence and efficiency. As they move beyond that, they apply these technologies to make their current products and services better, more customer-friendly, and more competitive than ever before. But the most innovative and risk-taking companies are able to move beyond those first two steps to invent entirely new products and services that wouldn't have been possible without these technologies. And of course, the most ambitious companies of all, often the startup companies that threaten the incumbents, are the ones that can rethink the entire relationship between company and customer to develop entirely new business models. And I'm sure you're all thinking of examples of these last couple of steps, the way a company like Uber has transformed what used to be the taxi industry, Airbnb, the hotel industry, and so on. What's new? Of course, using computers to make sense of data has been happening for decades. And so statistics, data mining, data analytics, all the techniques that allow us to tease information out of data, this is not new. But what's new is machine learning. With machine learning, we have algorithms that can build models from the data without being explicitly programmed. And this changes everything. It changes everything in a good way because now we can have models for processes way more complex than we could have ever developed on our own with traditional methods of programming. It means we're not limited by the knowledge we have of a problem and its solution. We have agnostic deep learning systems that can develop models from the data. But with this becomes huge risks. The old way of doing things, task-specific or rule-based programming, allowed us to understand in advance how the program was going to work in every scenario. But these deep learning systems are often called black boxes because it's hard to look inside and understand what they're going to do. And that's what I want to talk to you about, how these new powerful capabilities of machine learning help us, but at the same time, provide us with new risks that we need to manage. The new capabilities, of course, are extraordinary. We have computers that can now beat the world's best Go masters. We have robots that can help us with boring work or dangerous work. We have autonomous vehicles that hold the promise of making our commute hours more productive and our roads safer. But as we apply these sophisticated AI systems to mission-critical applications, these are applications where if something goes wrong, people die, and hundreds of millions of dollars or billions of dollars of damage occurs. AI systems are increasingly being used for commercial aircraft collision avoidance in the skies, for financial transactions, and to control the operation of massive power or manufacturing plants. And we can all think of examples already where AI systems haven't worked as intended and have caused serious problems and reputational problems for the companies deploying them, as banks and insurance companies grapple with the consequences of systems that may have bias in them, as autonomous vehicle manufacturers put cars on the road that sometimes crash into trucks or hit pedestrians. What we need are AI systems that are safe and reliable. Let me tell you what I mean by safe and reliable. We need systems where it's possible to verify through rigorous mathematical processes how the systems are going to work in every scenario. We need systems that are robust even when the input data is different from the data sets that they were trained on. We need AI systems that are robust against adversarial attacks, where the adversarial attacks might be in the training data or in the input data for deployed systems. We want to be able to audit our AI systems so that we can go back after the fact and understand why they made a decision, what the state of the system was at that time, so that if the system has malfunctioned, we have the ability to go back and correct it. We need explainable systems that can go beyond telling us a recommendation and explain the assumptions behind the recommendations, the scenarios within which that recommendation applies, and what some of the other possibilities were that the system rejected as not as beneficial. And we need unbiased systems that are going to treat all members of society fairly and in accordance with our society's values. Fortunately, some of the world's best AI researchers are now working on exactly these capabilities. And what I'd like to do now is give you some examples drawn from my colleagues at Stanford University to give you a sense of what the current research looks like in this area and how it will hopefully lead to safer and more reliable AI systems in the future. To do this, I want to take a look with you at 3 areas of current research. Work aimed at looking inside the black box of neural networks, at finding and then removing bias in AI systems, and assuring that autonomous systems like robots and self-driving cars are safe. Neural networks as you know, are the driver of the AI revolution. As I described, with neural networks, all you need is training data to set the numerical parameters. You don't need line-by-line programming. But neural networks are famously black boxes, and one of the problems is that there are too many paths through a modern neural network to be able to test every path by running simulations, even on the most powerful computers. So how can we ensure that neural networks will work as intended for every possible set of circumstances? In work by Clark Barrett, David Dill, Michael Kokendorfer, and their students at Stanford, they're taking a look at rigorous verification of neural networks. They've developed software called ReLUplex, which is an algorithm for error-checking neural networks. It blends linear programming techniques with SMT solving techniques. And the idea is to encode neural networks as a set of linear arithmetic constraints, a set of mathematical equations. The key insight of their work is as they test the huge number of paths in a neural network, to constantly evaluate whether perhaps it's mathematically impossible for the rest of the path they're on to ever be accessed. And if so, to note that and move on to the next path. And by doing this efficiently, they're able to scale to an order of magnitude larger network than any previous technique, which has now made it possible to test many neural networks on reasonable computers. And they believe this will allow them to discover the invariant properties of networks. In other words, the properties of networks that are mathematically true under every possible scenario, to prove a variety of properties of networks under particular circumstances, and to measure formal adversarial robustness. This means to actually put quantitative limits on how different or similar a malicious input data point would need to be in order to have the system respond badly to it. Let me give you an example of some work that they did with the Federal Aviation Administration on a piece of software called ACAS-X. A comment about where ACAS-X comes from. For the last few decades, the software that's stopped commercial aircraft from crashing in the sky, as many of you know, is called TCAS. This is a decades-old system that allows commercial aircraft to interrogate each other and give the pilot an advisory to climb or descend in order to avoid a collision. The FAA just announced within the last month or so that TCAS is going to be replaced with a new system called ACAS-X that uses a modern AI technique called Markov decision processes to do a much better job of commercial aircraft collision avoidance. The whole story of TCAS and ACAS-X is an interesting story in its own right, but it's not the story I want to share with you this morning. I want to talk about a variant of ACAS-X called ACAS-XU that's for unmanned aircraft, for drones. And the scenario being considered is in the picture on the right. Imagine that you're controlling a drone of your own. That's the one called OwnShip. That's the one that's going to be running this software. And imagine that there's an intruder drone. And the goal of your software is to make sure that you and the intruder drone, that OwnShip and intruder drone, don't collide. We're not imagining here that the intruder is trying to crash into you. We're not imagining that this is a missile or an enemy. We're just imagining that it's some benign drone and you want to avoid it if possible. And the FAA asked these researchers to use their ReLUplex technique to test several specific scenarios to see if they could mathematically prove that the ACAS-XU software would work as intended. Let me share two of these scenarios with you so you can get a sense of how this works. In the first scenario, they were asked to consider that an intruder is approaching OwnShip from the left, and they wanted to make sure that under every possible scenario of the intruder approaching from the left, the software would advise the OwnShip to steer strong right to avoid a collision. And in 1.5 hours, using moderate computing capabilities, the researchers were able to prove that an advisory to turn strong right is the only possible recommendation that can come out of the software. The second scenario was more complicated. The FAA now asked the researchers to consider that the intruder and the owned ship are at very different altitudes, and furthermore, that there had been a previous advisory for owned ship to turn weak left. And the FAA wanted to prove that the system under this case could only do one of two possible things: advise weak left again, or advise clear on course, meaning there is no imminent collision, continue in whatever direction you're on. And again, using moderate compute capabilities in 11 hours of computation, they were able to find a counterexample. They proved that there was a scenario where the system was not going to work as intended, and that then allowed engineers to go in and correct the code.
Doesn't that show that the intruder's approaching from the right, or do I have my right and left?
The picture does indeed. So the picture is just a cartoon to define the notion of two ships, and indeed, in any general case, you could have the intruder approaching from a variety of different directions. Thank you for that. In this next piece of work by Peng-Wei Ko and Percy Leong, they wanted to try to take a look inside the black box of neural networks. And the question they asked themselves was, given a high accuracy black box model and a prediction, can they understand why the model made the prediction? This is really important as we use AI systems for things like loan applications and healthcare decisions. We need to understand not only the recommendation, but the reasons behind it. And this can help to provide explainability, confidence, and better decisions. Their approach is to take a look at the training data and identify the training data points that are most responsible for a given prediction. And the key insight in their work is to use what are called influence functions, calculated efficiently using a technique called gradients. Here's one snippet of data where they developed and tested this work. If the picture on the left, when input into a neural network, produces the identification of dog, they're using these influence functions with gradients to understand which are the pixels in that photo that are most important, most heavily weighted in activating the neural network to come up with the identification of dog. If it's the pixels of that white dog itself, then we have a bit more confidence that the neural network is in fact responding to the dog in the image. But if it's the pixels that correspond to the sand or the ocean waves or the blue sky in the background, then we might be afraid that we have a brittle neural network, a neural network that might produce anomalous and erroneous results for different sorts of input. And I want to switch gears to the question of identifying and removing bias in AI systems, and I want to tell you first about some work by James Zhao and Londa Scheiberger. They point out that bias can result from two things: the training data, where some groups may be over or underrepresented, and they point out that the solution to this is to investigate how the training data is curated and what groups are represented in it. But bias can also result from the algorithms themselves. A typical machine learning program tries to maximize the overall accuracy across the entire cohort of input data, which will naturally lead to minority populations with small representation, to having less weight in the optimization than majority groups. And the cure for this is to understand how bias can be propagated and even amplified through these algorithms that seek to maximize overall accuracy. James Zhao and his students have studied this by taking a look at word pairings. This idea of word pairings is something that any 5-year-old can do well. Let me just remind you of how this works. The question goes, man is to king as woman is to, and any 5-year-old could tell you that the answer is queen. Man is to king as woman is to queen. Words can be represented as a vector in a very high-dimensional space, and the idea is, with word pairings, that the vector between two words, if it's the same word pairing, those vectors are congruent. So here on the right, you can see the two-dimensional projection of the vectors for these 4 words, and you can see that the vector connecting man and king is the same length and direction as the vector connecting woman and queen. This comes from a software algorithm called Word2Vec that's been trained on the entire Google News corpus. And at first blush, we would all think, gee, the entire Google News corpus, that's an awful lot of data. This must be pretty accurate. But of course, on a moment's reflection, we'll all realize that that will reflect society's biases. And let's take a look at how that actually plays out with a couple more word pairings. He is to brother as she is to. Again, any 4 or 5-year-old can answer that question. It'll be as she is to sister. So far, so good. But as you'll see in a moment, things rapidly start to go downhill, and then they become offensive and downright weird. We have he is to blue as she is to pink. That's okay, but now we start getting into trouble. He is to doctor as she is to nurse. Sorry. Sometimes just weird. She is to pregnancy as he is to kidney stone. I don't even know what's going on there. And he is to computer programmer as she is to homemaker. Absolutely offensive. And so what to do with this bias coming out of a large set of data like the Google News corpus? Well, what these researchers have realized is that in this high-dimensional space of word vectors, there's a dimension that corresponds to the gender subspace. And it's possible to geometrically remove the gender component from the words. And this approach to de-biasing is exactly what's used by Google, Twitter, Facebook, Microsoft, and others. But of course, it's not that simple, is it? Because we don't want to remove all of the gender information from everything. For example, there are some diseases that are correlated with gender. It would be counterproductive to remove the, quote, gender bias from something that none of us would think of as a bias, but we would all think of as just a factual attribute of the data. So this kind of debiasing can be very helpful, but it clearly needs to be done subtly and with sensitivity. In this work by Percy Leong and his students, they want to try to achieve fairness even when they don't have demographic information. The problem is that small groups have a low representation in minimizing the average training loss. But they point out that group labels are often unavailable. The group annotation may be entirely missing. Perhaps it wasn't collected due to cost concerns or a desire to preserve privacy. In many cases, the protected group might not even be identified or known. Their goal is to protect all groups, even minority groups, even when they don't have the demographic labels. And their solution is something called distributionally robust optimization, which is exactly what the words suggest. An optimization routine that works across all groups, whether majority or minority groups. Finally, I want to talk about safe autonomous systems. Autonomous systems like robots, drones, and self-driving vehicles need a way to explore the space around them, even though this space can be changing or might be unknown. Imagine a robot cleaning up your kitchen or your child's bedroom. Imagine an autonomous vehicle coexisting on the road with other vehicles. Work by Marco Pavoni considers how vehicles can evaluate by observing other vehicles and figure out if they're going to behave in ways that are cooperative, adversarial, or indifferent. Work by Dorsa Sadiq and Michael Kokendorfer tries to teach drones to do the sorts of things that we all do as intelligent drivers, where if we want to change lanes, we may nudge into a lane and then see if the drivers open up a space for us so we can continue in, or aggressively speed up, in which case we may go back into our lane and try again later. In the future, I think we're going to have safe and reliable AI systems enabled by these kinds of technologies. Verifiable AI systems that we can audit. Explainable AI systems that provide us with the reasons behind recommendations. Fair AI systems and the ability to detect and remove bias. And systems that are robust against errors, poor data, and malicious attacks. Research is providing the solutions to do these things. But success requires more than just these technological solutions. We need to implement them with care, and we need to decide as a society what our values are so that we can assure that these systems reflect society not just as it is, but as we wish it to be. Thank you very much.